Okay, hi everyone. So I'm Harry from the University of Bristol's Electrical Energy Management Group, and I'm going to give an overview of what we're doing looking at AM for next generation electrical machines. I should say now, especially as this is helped by AMRC, we're not looking at the development of AM in this, it's leveraging the technology through design, basically. I'm not going to spend too much time on this slide because we've just had a much more thorough overview than I could possibly give. But as we stated, to achieve our carbon net zero 2050 targets, we need to increase our power density to somewhere between 9 and 25 kilowatts per kilogram, depending on the year. Both from the ATI, but also the APC, which is the automotive equivalent in the UK. Those values are roughly the same. And we need to be achieving efficiencies of 96% or better. So it's going to be a challenge. That's a roughly 5-fold increase over the current state of the art. And I'm sure most people in this room recognize that that's a significant challenge. So if we look at the problem a little bit more specifically, and actually the questions we just had were a really nice introduction to this, so thank you. To achieve our step change in power density, looking at the electrical machine specifically, we need to improve efficiency, first and foremost. If we can reduce the losses inherently, then we have less heat, principally from what the losses create intrinsically. We can also raise the temperature rating of the machine, so we're going to have some losses, let's just cope with them a little bit better. And then finally, as is spoken about previously with the cooling system, how do we enhance heat extraction? And I'm going to go over a few of the things we're doing to achieve each of those today. But our general solution has shown so far, we've had a 20% reduction in loss, and that's obviously followed with a reduction in mass. And from both of those things, we've inherently improved power and torque density. But before I get into the technical side, I just want to say that this is our team at Bristol. There's 9 of us, with Nick, who couldn't be here today, being the lead academic. He's a senior lecturer, and he has a Future Leaders Fellowship through EPSRC. So this is his life now for several years. He's worked with FEMM on several feasibility studies and stuff previously. But also what you can see is that I myself, from the bottom left, I have no electric machine design experience prior to joining this group. My PhD was in additive and much lower cost additive. And with everyone else, my colleague George is here as well in the second row, we have a range of experiences that deviate from just electric machine design. And that's fundamentally because we need other technologies, again, as the ATI Kieran just spoke about, we need other technologies to help achieve our targets. It's not just about we can do something better with what we already have available. We need to develop several other technologies. Hence why we have such a broad spectrum. So these are our main sort of 8 stems of research that metal additive enables. The first is quite well understood. It's geometric freedom. I think everyone who's ever heard of additive manufacturing or 3D printing recognizes that geometric freedom is a massive benefit. But then there are several others, of which I'll talk about the top 5 today, that maybe are a little bit less clear, but that actually additive offers a really good opportunity to leverage. Some of the others, which I won't speak about today in great detail, if you have any interest or want to chat about, please do come and see myself or George later today, or follow up afterwards, and we'll more than happily talk about. But if I get into the technical side a little bit, this is the only maths we'll see. I know it's still reasonably early on a Tuesday, but yeah, that is the only mass we'll see. But hopefully you can recognize from the equation that thin conductors, where the width is much, much smaller than the height, shapes remain perpendicular to a magnetic field, will exhibit minimal loss. That's complicated slightly by rotor effects, meaning that that's no longer perpendicular to whatever slot you're using. So just laminating perpendicular to the slot doesn't work. We need to laminate perpendicular to the magnetic field. To do that, we've generated this algorithm, which I'm sure you probably can't read from where you're sitting, and I'm not going to go through in much detail, but there is a paper which is linked, but we can also give you, where using this time harmonic FE method, we start with a uniform lamination, which we then iterate through. So we develop a magnetic field or solve the magnetic field, shape our conductors, and then iterate through that loop, because obviously as we change our conductors, the magnetic field will change. What this means, and when we compare to uniform high fill and low fill distributions of conductors, is that we see a significant reduction in our overall losses just reshaping these conductors. Obviously, there's a slight DC increase compared to the high field because our overall cross-sectional area has decreased slightly. But on the whole, across the electrical frequency domain, we see an improvement. Similarly, our current loading, or power loading, for 180 degrees C average temperatures has improved by about 20%. Taking that a little bit further, we can then start looking at hybrid strand windings. So here we've just got a sort of, to be honest, reasonably naive additive manufactured design where, although it was additively manufactured, we're not really leveraging any of the benefits. And we can take that and take the conductors themselves right to the very edge of the slot. Through doing that, we have a thermal interface, which inherently gives us some cooling benefit, as well as increasing our cross-sectional area. But that inherently has downsides in terms of AC loss component. To improve that, we can then start splitting cross-sectional area up, and thereby reducing AC losses. Eddy current effects are reduced. Unfortunately, and similarly to what we were just saying about how we have losses, AC losses towards the rotor, due to the geometric positioning of each of those strands, we then have unbalanced strand currents, which effectively means they're not operating as efficiently and as optimally as we would like them. So we can take inspiration from Litz wire, which I can imagine most people here are probably familiar with, but that's effectively conductors being woven around one another to try and balance the loading through it. Unfortunately, we're working with conductors that are a little bit larger than the conductors you would find in sort of traditional Litz wire, and we also have AM considerations that we need to take into account. So although we can transpose, and we can do this in the end winding, so we can move where each of those strands are relative to one another, we can't do it in quite the same way. So there's a balance to be had there. Fortunately, the improvement is still significant. And so through this, we can balance our strand currents and see, relative to the baseline concept, we have a 40% improvement in losses and have effectively halved our operational temperature relative to atmospheric. Obviously, that allows us to push the motor harder or just use less energy in total, depending on what you want to do. We haven't made one of these yet. I'm very much hoping we will very soon, but at least the simulations are saying that it should be significantly better, and hopefully we'll have something to show you soon. Moving on to the next step, where instead of just improving efficiency, we want to try and extract heat from the conductor, we can start looking at thermal management. And the first part of this is recognizing that one of the advantages of additive is that we can reduce the overall package of the conductor. This is principally through reducing the size of the end windings, because we no longer have to worry about minimum bend radii or from the insulation of the conductor itself. Because of that, we can use that space to style and splay the end windings such that we can pass a fluid flow, in the instance shown it's air, over this to achieve cooling benefit, which reduces overall and peak temperatures. This can be taken a step further, and we're making one of these now, where we directly cool a turn. So we have a fluid inlet and outlet. We call it full terminal because we have the 2 electrical terminals, 2 fluid terminals. We directly cool the middle turn with 3 cooling channels. I don't know if they'll come up on the screen very well, but on the right-hand image at the very bottom, you should be able to see those channels. The reason that we're only cooling 1 is we've completed a previous experiment that shows that we can do it with a heat exchanger, which I'll come on to in a second. And in this example, it's right in the center, because this is only ever going to have DC applied to it, so our losses should be symmetric. In AC, this may not be the case, but we can move that turn as needed. But coming on to that heat exchanger concept, so here it's fundamentally the same idea. We're cooling a single turn using a heat exchanger. So instead of passing fluid directly through the turn is sized as it normally would be, but there's a heat exchanger built directly onto the end of it, all in one piece. Within that heat exchanger is this gyroid infill through which a fluid will be passed. I'll come on to how that gyroid was created in a second and the complications with that. But what that meant is we had 2 configurations for this conductor. When this conductor is made, it obviously has no insulation on it, it's pure copper. should say the example in the top left is copper and silver. It's just an example. The one we used was pure copper. It has effectively two configurations. Without insulation, we need to splay the winding. So there's an air gap between every turn to obviously avoid a short circuit. We can then insulate and compress that winding. So if we look at the insulated state, when we pass a fluid through it, we see that the middle turn cools significantly, as one would expect, but the outer turns see little to no real benefit. It's only through a very long conductive path, where the thermal conductive path is through the entire winding. When we compress that and insulate it, we see that the central turn increases in temperature, but our overall peak temperature, relative to the splayed version, drops by about 16 degrees, with an 80-degree baseline, I should say, and our average temperature reduction is about 2 degrees, again, relative to the splayed. Overall, compared to no fluid flow at all, we're seeing a reduction of between 25 and 30 degrees C, again, relative to that 80-degree baseline. So it's significant, and it shows that we don't need to cool the whole winding. We can be very targeted about the piece or the part of it that we do cool. This is currently not published. The screen's gone off, cool. Again, currently not published, but there will be a paper being published in hopefully the next 30 days or so, where hopefully you'll be able to read more about it. So if you follow us on LinkedIn or look at the university webpage or whatever, then I'm sure it will be there. If we go back to this dry rolled infill though, anyone who's used conventional CAD is probably looking at that thinking that looks horrible. I never want to design that in my life because it will take days without some automated way of looking after this. So in conventional CAD programs, we go from a vertex to an edge to a face to a solid to define a part. But what we need to start doing, at least for complex surfaces like that, is to start using something called functional representation. And it's kind of what it sounds. We use functions or a series of equations to define whether we're inside a part, on the surface of the part, or just in free space. By doing this, we can create very, very complex surfaces mathematically, which means that its file size is tiny, which although computers are getting better, is still often a problem. And we can repeat this surface for whatever spatial structure we like. The real complication here comes when we want to start mixing and matching boundary representation and functional representation and sending these to whatever manufacturing process we want. Because as you can imagine, the mesh for such a complex surface isn't particularly nice. So strategies to allow that more seamlessly is something we're working on. We're also here on the right-hand side looking at a heat exchanger experiment. So the previous heat exchanger that we showed where we achieved significant cooling benefit was just nominal geometry. It was something that kind of looked about right and worked for us, was manufacturable. But obviously that's not what we want to do when we're designing next generation electrical machines. We want to have an understanding around, okay, this is what I want to achieve, what geometry do I need to do it? So we're looking at several different gyroid infills, which again can be generated in seconds because of the functional representation. And we're going to measure the absolute temperature drop, or the power extraction, as well as the pressure loss over our working section. So that then in future we can hopefully size and design for whatever cooling effect we need. To do this, we're using a piece of software called Entopology. It's free to use for education, so if there are any institutions out there, please do have a look. But there's no reason that you can't do this yourself anyway. As I say, the equations are well known and understood. It's just we wanted to use an industry standard tool at the time being. This is a very light touch on some power electronics integration, where this was a feasibility study through FEMM, and I understand we're trying to hope to get another one in the works. But yeah, using additive manufacturing, as well as our conventional manufacturing techniques, we can integrate power electronics such as the inverter directly into the electric machine. This obviously saves on total volume and allows this sort of modularity of powertrain a little bit more. But yeah, AM fundamentally allows us to integrate cooling channels, which you can see on the bottom pictures, integrate terminals, fluid connections, and obviously yeah, provides us that modularity. This version is somewhat naive in terms of layout. We recognize that, as I say, it was a very early feasibility study, but hopefully we can start improving that over the next few months. So one of the other benefits I spoke about at the beginning was our ability to electrically insulate these windings in a different way. So fundamentally, that's because we're printing in place. So as we're printing in place, we no longer need to worry about cracking insulation or minimum bend radii. Because of that, we can start using, as I say, alternate techniques, and the first of which was just this dip varnish, dip varnish method, where we're very basically dipping it in some resin and then putting it on this multi-axis curing rig so that we can avoid drips and get a consistent layer. We're similarly looking at composites. This is a ceramic composite, so taking inspiration from what aerospace already do with gas turbine parts, and looking at using basically very, very high temperature, but obviously very brittle coatings. And finally, we're looking at, and the person who created this wanted me to say, this does exist now, it's not just a pretty CAD image, we have made it, but our lab is being refurbed, so the picture would have had mess everywhere in it, so I used the CAD image. But this is a 5-axis powder coater, CNC powder coater. So we can put our part on, it charges it, it sprays powder at it, and we should get a very, very consistent layer thickness across the part, which again allows us to use much thinner insulation, but hopefully achieve the required power ratings and thermal ratings that we need. So moving on to the challenges, just before I wrap up. Anyone who's used AM, whatever method, probably understands overhang supports, minimum feature sizes, minimum separation distances, post-processing, all a massive challenge. And not unlike any other manufacturing process, we need to start recognizing this very early in design. For us, what that's meant is starting to develop our own computational tools. So integrating DFAM rules, integrating very specific electric machine design rules into early computational design programs. And we're doing this for a series of open source CAD programs, as well as our own developed code. Fundamentally, the end goal is to have parallel CAD streams. So when a designer sits down and says, okay, this is my winding, what is it going to look like? We can say, well, this is what it will look like before you send it to the machine. This is what it will look like when it comes off of it. This is what it will look like pre-etching. This is what it will look like post-etching. This is what it will look like insulated. And run through that whole process seamlessly without someone having to sit there and manually model all of this. There are also challenges in electrical conductivity. For copper, we're now getting up to about 99% IECS. So it's becoming less of a challenge than it once was. That said, it's still very, very hard to make 99% IECS copper consistently. If anyone knows of a way, please do let us know. It'd be very useful. But obviously, it's still expensive. That is developing. It's not something we're actively developing, but obviously partners are. And it's found so far that there's very negligible build orientation dependency. Surface finish is a bit of a challenge. We'll come on to that. But aluminium is a little bit less mature. We're still developing this. And when I say aluminium, I mean very, very pure aluminium alloys, or pure aluminium, I should say. Fundamentally, this is just because they're both very reflective. And so it may be that we have to move to a different AM process. Similar challenges exist in porosity. This work is actually using porosity to our advantage. So Nick was at a conference last week in Valencia, which I forget the name of now, apologies. But this was using porosity changes to our benefit to control electrical conductivity through the part. I haven't got a reference to this, but it has, I understand, now been published. So if you're interested, I will get it for you. Just let me know afterwards. But it's also challenging. So this is one of the first heat exchanger prototypes we had made, and the one we did our testing on. We were getting a poor contact around one of the fluid ports, so we decided to chemically etch this, which again I'll just touch on really quickly. But when we put the chemical etching fluid in and wanted to wash that out, we put some compressed air in to push the fluid out, and we found a nice soapy liquid coming out the sides, because the porosity was high enough that it meant it was easier for the fluid to come out than run through our heat exchanger. We solved this with some araldite in the end, but hopefully we've got another one being made that will overcome that. I know I'm near the end, and I know I've spoken really quickly, apologies, but really quickly on surface roughness, it is a challenge with copper still, as it is with most AM processes. There are several post-processing techniques that can be used. We're generally using chemical etching, with some other advantages in terms of removing build supports and adding edge radii. But we obviously need to consider this very early in the process. itself, which we're doing with our computational tools. And to conclude, AM can significantly improve the available design space, can minimize losses, enhance heat extraction, and raise temperature ratings. But to do so, we need to develop the design methodologies and computational tools to enable that. But additive manufacturing, we think at least, can help to achieve our carbon net zero 2050 ambitions. Otherwise, thank you. I'm sorry for speaking so quickly. Hopefully there's some time for some questions, and if not, speak to myself or Nick, who hopefully will come back, and our emails on the screen.
Thank you very much, Harry. I think we have a couple of minutes.